Okay, let's see. It's recording. All right. Did anyone do some studying over the weekend? And yep.
I did do studying, but because for induction, I was trying to review that one thing, and like, you know how there's like a little arrow, and then it turns into like a drop-down kind of menu. Yeah, that link is broken.
Okay.
So actually, like, you know how they're all supposed to be like blue colored triangles? That one's like whited out, and even when I clicked on the induction link, it was, I don't know that.
Okay. Let me sign in first, then we can take a look at the link that it was grayed out. If it's grayed out from your perspective, it means, for some reason I'm hiding it or making it not available. Do you remember under which topic?
It was induction.
It was under induction?
Yeah, it was the whole thing. Like, I would click like to try to get to the drop-down menu, but I couldn't get to any of it.
Because I don't have any topics on induction. The only time when we talked about induction, do you remember the context? Where I used induction, or it's the proof of
Pascal.
It's the next one. I made use of the Pascal's identity. It's binomial. So it's the binomial theorem that we talked about, actual proof by induction. In other words, this is more or less kind of like a reminder for myself to talk about proof by induction. But the actual proof by induction is when we talked about the binomial theorem, which is in here.
Yeah, I saw that part.
Yeah, so this is the part when we actually talked about the binomial. Nope, not this one. This is the distribution, but this is the theorem. So when we proved the binomial theorem, we made use of proof by induction.
Yeah, no, I understand that. Because like when I clicked on induction, there was like 4 topics, but I couldn't access any of them. So there was like if you click on the actual link, there's like 4 topics, and I thought
under induction.
Yeah, like if you click on the induction, there's like 4. Like you see those 4 things that come up.
Well, those are topics. They're not supposed to be clickable. These are just topics for induction. Okay. All right. So getting back to combinations versus permutations, because I think there are some questions about that. So we'll go ahead and talk about that again, which is under discrete probability. Okay. Now I'm hoping that the notes that I just typed, like I did some more editing this morning because I have been trying to make this as clear as possible, in my mind, and hopefully also, help you understand all this stuff. So we'll go ahead and, start from scratch and talk about what a trial is. Okay, so a trial is one thing. It's a single attempt, one single thing. You flip a coin, that's one trial. You toss a dice, that's one trial. You pull one ball out of a cage, like in a Lotto, that's one trial. Okay? It cannot be divided into smaller chunks anymore. Is that okay? All right. Yep, go ahead.
Is the trial going to the data? Is the trial going to the data?
Go into the data.
Yeah, that we're going to analyze for the probability.
Yes, it is. It's one step of the experiments. I'll explain what an experiment is, down here. So the first one is a trial. Okay, the first thing we have to understand is what a trial is. It is also called an attempt. Okay, it is just a single attempt. But the key point here is it cannot be divided. Like, if you flip a coin, it cannot be divided into any smaller steps. It cannot be broken up into smaller trials. So it is a singleton or an atomic kind of thing. Is that okay? Some of your calculators have a random number generator, right? So when you click that button to get a random number, it's a trial. It cannot be broken up into smaller steps. Is that okay? All right. So typically it involves some kind of action, like flipping a coin, tossing a dice, drawing one ball out of a cage of balls in the case of lottery. But it always has a result. For example, throwing a 6-faced dice is a trial. Okay. Are there any questions about this part? No questions? All right. I'm just reaching into my pocket for a prop. So, okay, it is still a trial. It is still a trial because it cannot be broken down into any smaller steps. Okay. And it has a result. Okay, it has a result. So a trial, each trial has its own set of outcomes. In the case of throwing a coin, okay, the possible outcomes would be a set of either head or tail. In the case of throwing a dice, a 6-face dice, the possible outcomes would be a set of 1, 2, 3, 4, 5, 6. Is that making any sense? Okay? All right. So the next one is basically just repeating what I said. An outcome is, basically a possible result of the trial, which means in the case of a coin toss, if you really want to add, you can also say landing on the edge, so it's neither head or tail. But in reality, depending on the size or the shape of the coin, that should never happen. Has anyone actually seen a coin landing on the edge and doesn't fall over one way or another? You need a pretty deformed coin for that to happen. You have seen it?
I've seen it. It bounces off the floor though, and then it stops.
If it gets to the edge, it might rest on a wall like this, so it's not like completely flat. So each outcome of a trial is unique. In other words, a head and a tail are considered completely different. They're not the same. The numbers or the face of each face of a dice, I'm just using the numbers to represent the actual pattern on the dice, but each one is also distinct. They're not the same. Furthermore, the result of a trial has to be one of the outcomes in the set. Okay, and that's basically by definition, the set of all the outcomes is basically representing all of the possible outcomes. So you cannot have an outcome that is not in the set of all the outcomes. Okay, the set of outcomes has to include everything that is possible. So normally we have used this symbol already. We use omega, not related to big omega in the analysis of the timing of an algorithm, which is not in exam 2. Okay, so in this context, omega is really just a set representing all of the possible outcomes of a single trial in this case. Are we doing okay so far with just a single trial and the outcomes of that one single trial? Yep, go ahead.
I missed what you said about exam 2 on that. What did you say about exam 2 on this?
Exam 2 does not include the analysis of time complexity. Okay. So the master theorem and recursion is, hold on a second, that should be in the exam.
Right.
Yep. Graph theory is not in the exam.
Okay.
Yep, okay. Good job. Yep.
When I was looking at the exam, I didn't see anything on predicate logic. There was stuff about C and F and propositional logic, but I didn't see any questions about predicate logic. Was that just because you didn't put them on last year's test? Or?
That's just because it is still included in the scope.
Okay.
Yep. Okay, so are there any other questions before we move on to what an experiment is? Okay, all right. So now at this point we have the notion of a trial, which is doing something that can have some possible outcomes. But the key point of a trial is it is atomic. Okay, you cannot break it up into any smaller steps. And outcomes is really just everything that is possible out of a trial. So an experiment is defined to be basically just a sequence of trials. So things get complicated when a sequence of trials form an experiment. So if you throw a dice 6 times, or 4 times in this case, it is an experiment. Okay, so an experiment is a sequence of trials. Okay. You can also throw a coin 100 times. Okay, that becomes an experiment. The set of all the outcomes of an experiment is a little bit complicated because now it depends on a few things. So that's what the subsections here are for, because there are mainly 2 ways to arrange or 2 ways to look at the possible outcomes of an experiment. The first one is trial with no restrictions, or with in many cases it's called with replacement, which sometimes makes sense and sometimes it doesn't make sense. So I'll just use an example. Let's say you're throwing a coin, okay? So let's say you're throwing a coin 6 times. You flip the coin 6 times. After you flip the coin the first time, which let's say lands on the head, does that mean that all further trials cannot have your coin landing on the head? You cannot remove that option from further trials. So in that case, the quote-unquote with replacement part, it doesn't really make sense because we're not removing one of the choices because of an earlier trial. But in the case of drawing a ball out of a cage, in the case of a Lotto game, once you remove the ball from the cage, that is no longer available. So that's the only time when you have to think about, oh, okay, with replacement means we can put the ball back in the cage so that we can use the same ball again. Now that would not be Lotto, but you can imagine that there's a game like that. So in this case, with replacement, which means that we do not have restrictions based on an earlier trial, the analysis of the possible outcomes of an entire experiment, not of a single trial, is actually fairly easy, because in this case, I'm just using omega-1 to represent the outcomes of the first throw of a dice, and all the way up to omega-4, which is the outcomes of the fourth throw of the same dice. Do you guys notice that omega-1 and omega-4 are exactly the same? And that's because when you throw a dice, one throw of the dice does not remove a face on the dice, unless you have a really funky dice. Right? So that's why the possible outcomes of any throw of a dice is identical. You have all 6 choices available in each case. Is that okay? So when we need to look at all the possible outcomes, it really becomes just a Cartesian product of these omegas. Each one is basically the same thing, which is 1, 2, 3, 4, 5, 6 in a set. So now we have the Cartesian product of 1, 2, 3, 4, 5, 6 as a set, and do it to itself like 3 times. Are there any questions about this part? Because this is the simple part. Is that okay? Okay, let's think of another example. So if I want to consider all the possible ways that people can have birthdays in the class, so let's just say that we have 25 people in this classroom right now, okay, including myself. So if I want to say, okay, tell me all of the possible ways to arrange birthdays with a class like this, how would you do it? So each person becomes a single trial. I'm basically become a single trial where my birthday is one out of, let's say 365, okay? So let's not take that one, almost a quarter of a day into consideration. We'll just call it 365 days. So my birthday can be any one of the 365 days. Does that restrict the birthday of any one of you, the other 24 people in the class? No. So it is with replacement. As a result, what is the actual set of outcomes of this quote-unquote experiment? With 25 people in the class, I just need to look at all the possible arrangement of birthdays.
365.
Yep, becomes, well, the actual set is, basically each day of the year is in a set, right? So we have that set of every single day in the year, and then do the Cartesian product 24 times, so that we have actually 25 of them in a sequence. Is that making any sense? Is that okay? All right. Okay. Oh, wait, but is the ordering important? In other words, if we make this simple enough that we only have 2 people, okay, tag versus another person, is it important that I have, let's say, August 1st as a birthday, and then the other person has October 1st, versus I have October 1st versus the other person has August 1st? Are those 2 considered different?
Yes.
Yep, they should be different. Okay, so ordering is important in this case. Okay. So that's with replacement, which is actually easier to analyze, because when you look at the cardinality, what is the cardinality of one single omega-1 the way I define here? 6, right? Exactly, because we have 1, 2, 3, 4, 5, 6 in a set, so the cardinality of omega-1 is 6. What about the cardinality of omega-2? 6, okay? So we now have, basically each omega has a cardinality of 6. what do you think is the cardinality of the Cartesian product of these 4 omegas? It's a cross product.
24.
No.
6 to the 4th.
6 to the power of 4. Very good. Okay? Because when you look at 1, it has 6 possible choices. Okay? But that doesn't do any limitation on the second one. So that means when the first one is a 1, the second one has all the choices, 1 to 6. Okay? So as a result, when you just look at the Cartesian product of the first two, we already have 6 times 6. Okay? Then you look at this itself as one single bigger set, and then you say, okay, what about between this one and this one? Well, you have to multiply by 4, because for every element in this particular Cartesian product, it can be combined with any one of these 6. So as a result, when you look at the entire Cartesian product, the cardinality is the cardinality of 1 omega to the power of 4 in this case, because we have an experiment that has 4 trials. Is that okay? Any questions about this part? Okay, no questions. So this is the easy part. Okay, the difficult part comes in when the trials cannot have replacement. In other words, once you perform a trial, whatever the outcome of that trial is, that outcome is no longer available for all the further trials. Okay, so that's the more complicated one to describe as well as to model. Okay. So the first thing we notice is we can no longer use the Cartesian product of the set of outcomes. That does not work anymore. Okay. Now you might say, well, but it seems like that should still work because we can still use Cartesian product, but we can't, because Cartesian product means any element from the left-hand side can be combined with any element on the right-hand side. So there's no way to guarantee that we do not end up with the same element anymore. So in this case, I use omega x to basically represent all the possible outcomes of an experiment involving trials without replacement. So let me just kind of highlight the part that I'm talking about here and scroll it up a little bit so that we can all see this a little bit better. Okay. So omega, traditional is really just a set, but this time I parameterize it because, well, I need a parameterization later on to kind of define, how to construct this particular set. But at this point, we just need to know that, okay, x is representing all the possible outcomes of the first trial of this experiment. And omega x is representing all the possible outcomes of an experiment involving trial without replacement, and we want to use up every single thing in x. So how many trials do you think this experiment is going to involve? I start with the cardinality of x many elements for the first trial. So how many trials would it take to use up everything? So I have nothing left. Well, it's something about x, okay, but what of x? The cardinality of x, very good. Okay, so we have to conduct the cardinality of x many trials to use up all the elements of x. Does that make sense? Because each trial will take out one element out of x. So it will take me the cardinality of x many trials to use up every single thing in x. Is that okay? Sort of? Okay. Give you an example. Okay, so let's use mouse pad here. Okay, so let's just say that your x is 1, 2, 3. Okay, it is a set where the ordering is not important. So when you actually do experiments, okay, when you do a single experiment, which in this case consists of 3 trials, the outcome of the first trial can be a 3. Okay, but then the second trial only gets 2 choices left because 3 is already used without replacement. So the second trial can only be 1 or 2. Let's say we pick 1. So now that 3 and 1 are used in the first 2 trials, the third trial only get what? 1 choice left, which is a 2. So this is a possible outcome. Okay, so this is a possible outcome out of choosing 3 things out of 3, but in a way that is without replacement. Is that okay? When I use parentheses like this instead of braces like this, what does it mean? What is the difference? Ordering is important. Very good. So that means this sequence is not the same as this sequence. When you return is not the same as this sequence, and so on. Okay? So they're all considered different. Are there any questions at this point about what it means when I say without replacement? Once you take out one particular outcome, that outcome is no longer available for the further trials. But how do I enumerate all these possible outcomes? That becomes a problem because I cannot use Cartesian product anymore, which is the easy thing to do. So the first thing I do is, I'm going to use a recursive way to look at this. Okay, so the recursive way to look at this is, what if x is empty? If x is empty, which means we do not have anything left, okay, and I say, well, go ahead and do an experiment, do one trial anyway. What is the outcome of that trial when you don't have a choice anymore? There's nothing to choose from. Nothing, exactly. It's like, you have no coin, okay? I do not give you a coin, you do not have a coin to begin with, and I ask you, okay, tell me the result of flipping that coin. What are you going to tell me? There's no result because you don't have a coin to flip. Okay? So is that making any sense? The big omega of x when x is empty is just the empty set. We don't have any outcome to talk about. Is that okay? All right. So the next one actually makes more sense. The next one is basically saying, what if the cardinality of x is exactly 1, and I ask you to tell me what is the outcome of this particular trial when you only really have one thing to choose from. Well, then it has to be itself. There's no other way. Okay, imagine this. Okay, I give you one little card that has a number in it. Okay, and I say, okay, put this into your hat. Okay, just imagine you have a hat if you don't. Okay, and I say, okay, put this in your hat and draw a random card from your hat and tell me what that number is. But all I did was to give you a single card with a number. So what do you think is the outcome? Well, it has to be that same thing that I gave you, right? So that's why in this case, if x only has one single element, then omega x has to be x itself. There's no other way to arrange it. Is that part making any sense? Okay. So these two kind of make sense because we're dealing with an empty set and we're dealing with a set with only one single element. And remember what omega stands for? Omega is saying, okay, give me all the possible outcomes of trials involving the set x. But when x is empty, there are no trials possible in that case. When x only has one single element, then you say, well, whatever you gave me is the only outcome that is possible. Done. Okay. So what if x is a little bit bigger? What if x has more than one element? Well, in that case, we have a slightly more complex way to define omega x. So we say omega x is, okay, this notation is basically just saying a whole bunch of unions. Okay, it's basically saying for each e as an element of x, do the following, and then we'll do a big union of the following. Is that okay? So I can expand this for throwing a dice. Well, we'll say throwing a funny dice because when you're dealing with the dice, it is always with replacement. So we'll phrase it differently. But we'll go through this equation first. So what are we doing with each e in x? What we're doing is we say, okay, let's make a very small set, a singleton set, or a set with only one single element, with just e. Which e are we talking about? Whatever e you choose as an element of x. Okay. So this e is we're making a set out of e with only that one single element. And then we do a Cartesian product here with something. Well, we're using a recursion here. Okay, the recursive part is to say, let's do Cartesian product with this particular set. What is that set? Well, let's not look at omega first. Let's just look at this part here. What is x minus curly brace e? What is that really saying?
Just removing E, bro.
We are removing e. It's the same thing as x, except e is no longer in it. Okay, it's almost exactly the same, except e is not in it. So what is omega of that particular set? All the possible outcomes of all the outcomes except for e. Is that okay? All right. So when we combine that with e, then we have the entire sequence. Is that okay? Okay, let me scroll this up, and then we'll do a very quick run as an experiment. Okay. So here we'll take a look at, we'll just use this x here, okay? So we'll say, okay, what is omega of x? So omega of this particular x is exactly 1, 2, 3, right? Okay. So how do we spell out everything at the top level, okay? So at the top level, we'll say, okay, for each element e of x, do the following. How many items are we talking about here? How many items do we have in this particular union, but applied to the set of 1, 2, 3? E can be 1, E can be 2, E can be 3. So we have 3 terms. Is that okay? Okay. So the first one is, okay, let's look. So I'm going to use parentheses here, just so that we can spell out the overall structure of this particular set first. Okay? Is that making any sense? The first one is when E is 1. The second one is when E is 2. The third one is when E is 3. Is that okay? Right? Okay, so with this one, we are now dealing with the set of just 1 by itself with a Cartesian product of omega of, what do you think is this particular set here? It's the same set as the one that I started off with, but with the element removed.
2 and 3.
It would only 2 and 3, exactly, because 1 is already used here. And then in the second line, we have, and let's say, what if E is 2? Then whose omega am I trying to find out here? What do you think would be in this particular set?
3.
1 and 3, right? Because in this case, 2 is used. And what about the last one? E equals to 3, right? Or the set, well, E is 3, so we're considering the set of just 3 itself. Cartesian product with the omega of, what do you think is in here?
1 and 2.
1 and 2, because 3 is already chosen, so we only got 1 and 2 left. Is that okay? And then somebody will say, but we're not done yet. Okay, what is omega 2, 3? What is omega 1, 3? And what is omega 1, 2? Well, we'll figure those out, right? Because the definition itself is recursive. So we go down here, and then we ask the question, okay, fine. What is this then? Well, it is the union of 2 particular sets, right? And what about the first one? It's the set of, well, you can pick 2 or 3 first because it is a set, it is not ordered. But I'll just use 2 here. And it's going to be crossing Cartesian it's a Cartesian product with 2 as a set with omega of what?
3.
Just 3 by itself. And over here we have 3 times the omega of which set? 2, right? Okay. What about the others? What about this line here? Very similar. Okay, so I'm just going to expand one to finish it. The other ones are very, very similar. Okay, so now we have boiled down to omega 3 and omega 2. Okay, so we say, okay, what is the omega of just the set of 3 by itself? Well, haven't we seen this one before? It's a set of only one single element. So that's kind of special because we don't need the recursive definition anymore. What is the result of this?
3.
Exactly just 3, right? And then omega 2 is just the set of 2. Is that okay? Yep, go ahead.
So this is finding us all the possible outcomes?
Mm-hmm. But we want to plug these back in and see if it makes sense, okay? So now that we know what is omega of the set of 3 and the omega of the set of 2, let's plug it back here. I'm not going to erase it because I don't want to get rid of that. So now we can go back and say, oh, we know what this is. This is just 3. And we also know what that is. It's really just 2, or the set of just 2. Is that making any sense? Oh, but don't we know what this is really about? Because the Cartesian product of the set of 2 and the set of 3, because each one only has one single element, isn't that really just 2, 3 as the first thing? And then the second one is really the set of 3, 2 as a 2 tuple? Is this part okay? Because we look at the definition of the Cartesian product. You choose one from the first set, you choose one from the second set. Well, the first set only has one element. You don't really have a choice. The second set also only has one single element. You don't have a choice either. So you have to choose 2 as the first element of the 2 tuple and choose 3 as the second element of the 2 tuple. And that's the only 2 tuple we can make. Okay? Same thing applies to the other one. So what is a better way to spell out 2, 3 as a 2 tuple as a set union with 3, 2 as a 2 tuple in a set? Is there a better way to spell this out? Can I do something like that? Because it's the union of 2 different sets, right? And because the elements are completely different, I'm just going to add everything together. Is that okay? All right. So given this is omega 2, 3, can someone give me a quick guess, okay, as to what is omega 1, 3? What do you think that's going to be? The set of 1, 3 as a 2 tuple and 3, 1 as a 2 tuple. Is that okay? Okay. And the other one is, okay, we'll just go through this just to be complete. 1, 2 in the set. This is going to be 1, 2 and 2, 1 as 2 tuples. Okay. So now that we have figured out what is the omega 2, 3, omega 1, 3, omega 1, 2, then we plug everything back into this thing, okay, and say, okay, what is this becoming? Well, we take out this, and we substitute it with this thing here. Is that making any sense? I'm just doing substitution. Once we find out what is the recursive smaller problem, once we know the solution to the smaller problem, we can now say, okay, we can just plug that back in and figure out the solution of the bigger problem. Okay. Is that okay? This is just purely a substitution based on how we resolve the smaller omegas. Is that okay? So now we look at this and go like, oh, that's a pretty easy one, because even though the right-hand side of the Cartesian product seems to be a little bit complicated because it has got 2 elements, what about the other one? What about the one on the left-hand side? It only has one single element. So how many elements are we talking about when we look at the actual Cartesian product of this thing? It only has 2 elements, because we can combine the 1 on the left with 2, 3 on the right-hand side. You can also combine the 1 on the left with the 2, 3, with the 3, 2 on the right-hand side. So you end up with 1, 2, 3 as a 3 tuple, and 1, 3, 2 as a 3 tuple of this part that we have just highlighted. Okay. So now we can say, oh, okay. So given that is the case, then this whole thing is really just 1, 2, 3 as a 3 tuple, 1, 3, 2 as a 3 tuple as a set, union with the second line. Okay, so we are now dealing with the second line here. What about this guy? What do you think is the result of this? It's a set of 2, 3 tuples, And first one, okay, because it's a set, you can choose whichever one comes first, okay? But just going with the same type of ordering that we are going with, the first one is going to be 213 as a 3 tuple, and 231 as a 3 tuple as a second one. Okay, so we have 213, combining this 2 with the 13 as on the right hand side, and 231, combining the 2 with the second element in the set, like so. And the last line, I think by now we probably can guess what it is. 312, 321, like that. Are we still okay so far? Okay. Oh, well, it's a union of 3 different sets, and they do not share any common elements, right? Because in the case of 3 tuples, the ordering is important. Everything on the first line starts with 1, everything on the second line starts with 2, everything on the third line starts with 3. They cannot have common elements. So as a result, now we have one bigger set where we just say, okay, we'll just put everything into this set as the actual union of the entire thing. So we just put this here. And the last one over there. There we go. Okay, I just made this a little wider so it looks better. There we go. Is that okay? So now I have a recursive way to define omega that generates all the possible, are we talking about permutations or are we talking about combinations here? Permutations, because ordering is important. So we are generating all the permutations. Woohoo! Okay, so are we okay with this part? Can I switch back to the notes? So this is just an example illustrating how the recursive definition works. So in the notes here, okay, I proceeded to talk about, okay, sometimes you do not necessarily want to choose all of the elements. Think about Lotto, okay? If you think about Super Lotto, how many numbers can we choose from as the first trial? Is it 42? I cannot remember. Does anyone remember? Nobody plays Lotto after the first class or second class. Okay, I'm gonna look it up. Super Lotto, and it has a place that talks about how to play. So how to play? There we go. Okay. 47. Okay, so 1 to 47. So in this particular case, we don't really want to generate sequences of 47 numbers. That's not how the game is played, right? We only need to pick, in this case, pick 5 lucky numbers. So let's not take into consideration the mega number, because that really is not a part of the combination versus permutation consideration. So we'll just take the first 5 lucky numbers, okay? 5 lucky numbers from 1 to 47. So we are actually picking only 5 things out of 47. So the way I defined big omega, not big omega, just omega, is not going to work, because this definition of omega will only stop when the set that we're considering only has one single element left. That's not going to work in the case of Lotto. So I'm going to change the definition just a little bit so that we use this notation here that says, okay, omega xn in this case is the set of all possible outcomes where the first trial, in this case, has the set of x as possible outcomes, but we want to have a sequence of n elements. Is that okay? So I'm parameterizing what we had earlier with a second number, basically to limit how far we should go. Is that okay? So using this kind of slightly changed or refined definition, then we can still stop the recursion and earlier too. Because in this case, all we have to do is to say, oh, you know what, when n equals to 1, which means, just give me all the possible outcomes when the first trial has x as a set to choose from, but we only need we're only dealing with one single trial. Okay? What would be the set of possible outcomes with one single trial when x is representing all of the possible outcomes? So once again, imagine you have a hat. Okay, many of you do not have a hat today, but just imagine you do have a hat. And I give you, okay, here, this is a bunch of numbers that you can choose from. Okay, drop it in your hat and give me a number. But what are the possible outcomes?
All of the numbers in the hat.
Exactly, because that's the only trial you have to deal with. So that represents, so X once again is the result itself, which is representing all the possible outcomes of this one single trial. Because I'm only interested in, guess what? One trial, n equals to 1. Is that okay? So this is in terms of recursion, this is the part where we stop doing the recursive call. What if n is greater than 1? Well, if n is greater than 1, then we use something just like before. Okay, you can see that the recursive definition is almost exactly the same, except we also have to take care of the number that we're passing to the next invocation. So in this case, we just say, oh, the next invocation, you have one less trial this time, because I just took care of one. So you can deal with n minus 1 trials. But using this particular definition, we can now say, oh, okay, so we have a way to basically say we start off with 47 numbers in the case of Lotto, and we just need 5. Okay, so we have an experiment with only 5 trials, and each trial without replacement, but we have a way to generate all the possible permutations of choosing 5 balls out of 47, or choosing 5 numbers out of 47. But we are still dealing with permutations, where 1, 2, 3, 4, 5 is considered different from 5, 4, 3, 2, 1. Is that okay? Because each element of this omega is still a 5 tuple. When you're dealing with tuples instead of a set, ordering is important. So are we still doing okay so far with this? Yep.
I don't understand, is this going to give us the number of total possible outcomes?
Nope, it will give you the set of all possible outcomes. So the cardinality of that is the number of possible outcomes.
Okay.
So most of the time we're not really interested in the actual set itself. We are more interested in the cardinality of the set. Mm-hmm. But here, I just say without proving it, okay, so we can prove it. Well, that would make a pretty good question in the exam, but we can prove this. And I'm just saying that the cardinality, I missed one thing here. It is not the set itself, it is the cardinality. I better fix that because I don't want any confusion. This is actually how I write the notes, which is a little bit harder to find how to change something because it doesn't resemble what we're actually seeing on the screen. So we are looking at the cardinality of the omega. And we'll do a save and display. There we go. Scroll back to that spot. There we go. So now we have the cardinality of omega xn is permutation, choosing n out of bar x bar, which is the cardinality of x. So if I ask you to prove this, how are you going to prove that? What technique are you going to use? So let's kind of go back to the 3 big families of proof techniques, 4 to be exact. One is proof by contradiction. Am I asking you to prove this is wrong? Well, if I'm not asking you to prove something is wrong, proof by counterexample is not going to work. Okay. What about a direct proof? A direct proof is going to be pretty hard because a direct proof usually doesn't do very well with recursive definitions. So now that we know there's a recursive definition here, what does that remind you of as a proof technique? Proof by induction, very good. Okay, so proof by induction and recursive definitions, they go hand in hand. So if I really want to prove this particular theorem, okay, which is just this part here, if I want to consider that as a theorem, the first thing I would notice is to say, oh, okay, if this is the theorem that I need to prove, I look at the definition of omega, it is recursive. And the first thing I would do when I'm dealing with a recursive definition is to think of base case, exactly. And the base case is when we stop recursion, which is this one here. Okay? So once I know the base case, then I can use the induction step, right? So the induction step is saying, okay, if I know that when we're dealing with, we basically just say the n is some number. We just need to prove it for the next one. So let's say n equals to k. We assume n equals k already has the property like this. Then we want to say, what if n equals to k plus 1? That's basically what we're looking at. And that's pretty easy to do because when we already know omega k minus 1, we kind of use this and say that, oh, the parent or whoever is calling that is going to have k plus 1 elements in the set, which means we'll have k plus 1 of these individual terms, and then each one of the subterm is permutation choosing k out of the set itself is also smaller, so you will have to kind of take that into consideration. Okay, does anyone want to do this one? Yeah, just kind of do it, proof by induction, because I want to do it. Yep.
I do too.
Okay, so let's do it. Okay, so let's go ahead and do this one. Do it by proof by induction, because I don't like to, I really hate to say without proving it, the following theorem is true, so let's go ahead and do it. Besides, this is also a good opportunity to review what is proof by induction and how to apply proof by induction in this case. Okay. So what we want to do is to prove that bar, okay, I have to spell omega because there's no omega key on the keyboard. And this is permutation of bar x bar n. Okay, there we go. So this is the theorem. But we're also given some assumptions. If you go back to the notes, okay, I'm just going to switch back to the notes just a little bit. We'll switch back to the other one. I already tell you the n is always less than or equal to bar x bar, which makes sense, okay, because otherwise, things won't work out. Because we'll then be trying to pick out more things than there are things available, which doesn't make sense. So n is always, so given that n is less than or equal to bar x bar, okay. So that's a given already. All right, so we'll do it by proof by induction. Okay, so we will say proof by induction. There we go. Base case. Base case. The base case is when we are dealing with the cardinality of omega x, and we're dealing with 1 here. Okay, so we'll just say n equals 1. Just to be extra clear, this is by definition bar x bar. But does it fit the theorem itself? Okay, that is the question. Does it fit the definition of the theorem? In other words, what I'm asking is, can I establish this? That is the question. If I can establish this equality, I have just proven the base case.
Are you using a cardinality on the left-hand side of the equation?
Oh, yep, I'm missing the right-hand side of this cardinality here. Okay, so let's see what we can do about this one. By definition, we know this is the same as that. Right? Okay, okay, let me try not to be this lazy. Okay, so this is by definition. We know this part because this is the end case of the recursive definition. Is that okay? So are there any questions about why we have this established equality?
Because it's in our iota.
Say again?
Because it's in our iota.
It is. It's the definition. We are not dealing with propositional logic nor predicate logic here. We're just dealing with good old, math proof here. Okay. What about the other one? What about the P of bar x bar 1? How do we define permutation? Does anyone remember? Okay, maybe we should revisit that. Okay. So the permutation of choosing r out of n is what? Okay, come on, you guys should remember that. N factorial divided by n minus r factorial. Very good, good job. Okay. So when we plug the definition of permutation here, then we get the p of, okay, we already know what that is. So we have basically bar x bar, x factorial divided by bar x bar minus 1, that whole thing factorial. Right? This is just plugging in the n and the r. And what is that? What do you think that is? Well, let's spell this out a little bit, okay, and see if we can figure it out. So we'll say, okay, what is bar x bar factorial? Well, bar x bar factorial is bar x bar times bar x bar minus 1, the factorial of that. Okay, is that part okay? Can everybody see how this product is really just bar x bar factorial? Is that okay? Okay, so, and then we keep the denominator like that. Wait, isn't that really the same thing as that? Yep, so we have the same term in the numerator, which is what I'm highlighting here, and also in the denominator. So they cancel out each other to 1. So what do we have left? We just have bar x bar left. Okay, wait, hold on a second here. We have just proven this part because of the definition of omega, and we have proven this part here because of the definition of permutation. But doesn't that mean that we can now establish this thing equals to this thing here? They're both connected to bar x bar, but now we have established this particular equality, right? Okay, so we have just gone through a lot of mechanical stuff, a lot of definitions and whatnot. So we have, that's the how. What is this? This is the result of the base case of proof by induction. And why is that important? Because proof by induction won't work unless you have a base case. And now we have a base case. Is that okay? All right. Yep, go ahead.
So is the base case what you have on the top there versus by definition or on the very bottom?
You mean this part here?
Yeah.
This is by definition.
Okay.
This is by definition because of the way. Okay, let me go back to the notes here. And I hate to flip flop a lot, but this is the definition.
Oh, okay.
So when you take the cardinality of the set of the right hand side and take the cardinality of the set on the left hand side, they should be the same. So I'm using this. Okay, I guess it's not exactly by definition because the definition only deals with the individual set. But when you take the cardinality of two identical sets, then the cardinality should be the same as well. So I guess I skipped one step.
But then on the bottom there, you proved that is our base case.
Yes, this is basically saying, now we have just proven that. Because we basically have two steps here. The first one is by definition, we know this one. And then the second one is to use the definition of permutation to establish that. But since they both end up with bar x bar, that means this part here is the same thing as this part here. And that's why we have the actual equality that we need as a base case. Is that okay? Okay. So now that we have a base case, we can now start to work on the induction step. Okay. So now we work on the induction step. Now the induction step always starts with an assumption. Okay. We basically say, well, we assume that the theorem is true for cases up to k. Okay. N equals k in this case. So we can say that assume the theorem is true for cases. Okay. So we say, okay, so we'll say that this is true for omega x, n equals k in this case, equals to the number of, equals to the permutation of x bar, comma, k, like that. Okay. So what is our objective? Our objective is to step this up to prove that this is also true for omega. Okay. Need to prove this is also true for omega x n equals k plus 1. We just need to step it up by 1. Okay. Equals to that. Okay. Now, I probably should not be using the same x here, okay, because they can be different. Okay, so I'm going to choose to use a y here instead of x just to avoid that confusion. Okay. Because the set is not the issue. It is the n that is the issue here. When we say that the cardinality of omega x1 equals to p of the permutation of bar x bar 1, we didn't put any limit on x. As long as the set x has at least one element, that should still work. Is that okay? So as a result, when we work on the induction step, we also should not be locking down the set itself. So we basically say for all sets, as in the case that the cardinality of x is greater than or equal to k, this is true. And now we want to prove for the cases where for the omega of y, where the cardinality of y is at least k plus 1, we also want to know whether this equality holds or not. Is that part okay? So we're not locking down on the set itself, we're just locking down on the number, or n. Okay. All right. How are we doing this? Well, we're going to do this based on the definition of omega first. So now we say this is the union. Okay, this is the union. And I can't really do the subscript thing using a regular text editor, so I'm just going to use a underscore to mean the following is in the subscript. E in y in this case. And then I'm just copying the definition, by the way. It's nothing new. This is a E Cartesian product with omega y minus the set of E, and then we have k here. Okay, is this part okay? This is just by definition. This is by definition of the omega function. Is that part okay? Okay. But in reality, we're not really interested in the set. We're interested in the cardinality. So I am just going to put, this part needs the cardinality here. So we're only interested in the cardinality. So we have to keep using cardinality for all of the other ones. Okay, so we are looking at the cardinality of this. When running out of space again, I can make this just a little bit wider. Nope, not wide enough. But that's still okay. So we'll just make sure that we put a cardinality here. Okay, so when we look at the cardinality, and this is a Cartesian product, right? How many things do we have in this union? In other words, how many elements do we have in Y? The cardinality of Y, right? The number of elements of Y is the cardinality of Y, okay? So we can say, okay, so we have this, okay? So when we look at the cardinality, okay, let me see how I can look at this in a certain way. Okay, first of all, for each y, is there a chance that this particular set, okay, can share elements with another one like this? Okay, scrolling back up, okay, let me scroll up a little bit. So the question really is asking, Okay, looking back at this one, the question is asking, can this particular set have any common element with the second one? Because if they do have common elements, then I have a bigger problem to solve, because I have to find out, okay, now that we're doing the union, we have to subtract the common elements. But if they don't have common elements, then it's easy to count. But how come they don't have common elements? It has to do with, can they start with the same thing? They do not start with the same thing. Well, if they don't start with the same thing, and this is a Cartesian product, what is the result of a Cartesian product? How do we call it? Do we end up with a set? Tuples. Exactly. Each element in the result set is a tuple. But in a tuple, ordering is important. Does it make sense? But since the tuples from, okay, I have to use the highlighting here. The tuples ending up here, they all start with 1. The tuples ending up here, they all start with 2. Can there be any intersection? Well, the intersection is empty. There are no elements that are common with these. Okay, which makes counting a whole lot easier, because now the cardinality of this is really the cardinality of this plus the cardinality of this plus the cardinality of this. Is that making any sense? But how many rows are we talking about? The number of rows that we're dealing with is the same as the number of elements here. Is that okay? Yes? No? Yes? Okay. All right, so we'll do it step by step. Okay? So in this case, we're going to do a sigma. Okay, so we are taking out the cardinality out of the overall thing, so that we now end up with a sigma as a summation. Okay, yep, go ahead.
I'm kind of confused on how you got to that last where it says union, how you got from the step above it to there.
Oh, they are actually not related, because, okay, let me make it clear. So this part is the question, can we establish that? Okay, but this part is actually by the definition of omega. That's by the definition of omega. This is the question. This is what we want to be able to prove. We want to establish this equality, but we are not there yet. This is our goal, our objective. Okay, so I'm using the sigma notation, E and Y. And then for each sigma, I'm going to use the actual notation of cardinality. Is that part okay? I'm changing the union inside the cardinality into a sigma outside of the cardinality, because I'm just adding the cardinality of individual items of this union. Because I know that these things in the union do not have intersections. As a result, I can just add the cardinality of each component instead of having to actually go through the union. Is that okay? All right. So we now move the cardinality into each individual part, which is bar E bar times omega y minus E k. And I'm just checking on the nesting of parentheses here, making sure that that is still okay. Oh, omega is misspelled. There we go. Yep, go ahead.
How come that's not k plus 1 in the omega?
How come what is not k plus 1? The k plus 1 is here. So I am given the problem of dealing with sequences of k plus 1 things in a tuple. So the sub-problem, I'm subcontracting out those problems as k because of the recursive definition. Mm-hmm. So is this part okay? Connecting this line to this line here. Is that okay? All right. Okay. All right. So I'm not going to deal with the sigma for the time being, so I'm going to keep the sigma out here. Okay. We are looking at the cardinality. Okay, this is the cardinality of a set that only has one single element, with a Cartesian product of something that has some number of elements. So what do you think is going to be the cardinality of this entire thing? Or in general, okay, what is the cardinality of a Cartesian product of two different sets? Well, not necessarily different, two sets. Okay, let's go back here. Okay, so let's work it maybe down here a little bit. So if I have the Cartesian product of A and B, okay, what is the cardinality of the Cartesian product of A and B? Any set A, any set B. What is the cardinality of the Cartesian product of these two related to the Cartesian product of the first one and the the cardinality of the first and the cardinality of the second? Exactly. It's just a multiplication here, right? Very good. Okay. So it's just a multiplication here. Does this apply to every single set out there for A and B, or does it only apply to some? What if A is empty? What is the cardinality of an empty set? 0. Okay. So is that true? If I do a Cartesian product of an empty set with something else, is that an empty set? It is an empty set because the Cartesian product means pick one from the first, pick one from the second. If one of the two sets is empty, there's nothing to pick. You have an empty set. Okay. Okay. So this is actually a part of the algebra of set operations. So I'm going to make use of this over here, because in this case I have a set with only one single element. What is the cardinality of a set with only one element? 1. Very good. And do we know the cardinality of this guy here?
That was just the cardinality of y minus 1.
No. Remember, the set itself is not really the big issue. The whole thing about this is what is k, or n equals k in this case. Don't we know something about the case when n equals to k? Or I should say, didn't we assume something? As a part of the induction step, we make an assumption. What was that assumption? We assume the theorem is true when n equals k. We want to prove that it also works for n equals k plus 1. But the assumption is, okay, let me scroll back up because I definitely wrote that down. Induction step. Assume the theorem is true for cases. Okay, I forgot about the cardinality again. There we go. Okay, if that is assumed, can we use this assumption? Yes? No? But this is the key. This is the most important part about this particular proof, is to make use of the assumption at the beginning of the induction step. Okay. So now that we know this part here, so we can always come back and explain this again, but we can now say that, hey, okay, we'll do it step by step. Okay, we'll do it really step by step in this case. So I first break out the individual cardinalities. Okay, so we break out the cardinality of a Cartesian product into the cardinality of the individual parts with a regular multiplication in between. Okay, so let's do it really step by step here. Okay, that is right. Okay, so is this part okay? To change it from this into this is really just using this particular thing here. Is that okay? So take it to the next line here. Okay. We know the cardinality of a set that only has one single element is just 1. Okay, that's pretty easy. So now our biggest worry is, but what is that thing? But because of the assumption at the beginning of the induction step, we know what that is. Because of the assumption in the induction step, we know that part is really just that. So now we are dealing with, okay, So we can now rewrite this part as the permutations. And in this case, we are choosing out of y minus e and the cardinality of that. And we are choosing k out of that. I'm just matching the number of parentheses. Okay, there we go. But this is the most important part of proof by induction, is making use of the theorem, of the assumption earlier, to establish this particular part here. Without the assumption earlier, I would not be able to make this change. And this is really the most important part. Are we still doing okay so far with this? Sort of. Do you guys remember, how we kind of visualize proof by induction? You have a base case, which is a spot that you can land on, right? And then the induction step is basically saying, let's say that you're on one particular step. Okay, you're not in quicksand anymore. The induction step basically means there is a way to move a step ahead. That's what the induction step is really talking about. Is you're on one solid ground square, and you can make a move to the direction that you want to move. Is that okay? So what we are using here is to say, oh, we are on a solid step already. The solid step is making this link here. So the question is, can I move ahead one step? Is that also a solid step if I just take it one step ahead? So now we are trying to establish that. Okay, so I'm gonna make this a little bit easier. 1 times whatever is just whatever. That part is easy. I don't think people have any problems with that, right? Okay. So now we have this summation on the outside, and then we have this thing in the inside. But would this term change depending on which e I choose from y? Because we are not looking at the individual set, we're just looking at the cardinality of those particular sets. So it doesn't really change. Okay, I can pick the different e in y. It wouldn't change this number. Is that okay? So how many elements do we have in e? Excuse me, how many elements do we have in y as a set? How about that? Is that okay? Because we have bar y bar terms, each term looking exactly like this. So if we have bar y bar terms and each term looking like that, oh, why don't we just, instead of saying summation, same thing, plus something, the same, plus something, exactly the same, why don't we just say it's a multiplication? Is that okay? Because we are actually adding up, okay, let me go back here and highlight it. We have bar y bar terms of these things. They're exactly the same, but they're bar y bar number of those. And we are using sigma originally, which means we are saying this plus this plus this plus this, do it n bar y bar term times. Okay, that's just a really bad way of spelling out multiplication. So instead of spelling out everything in addition, we just say it's just a multiplication. Is that part okay? Kind of. Are we okay? All right. Okay. So when we have this, let's go ahead and change this a little bit so it's easier to read. I'm looking at the cardinality of the subtraction or the difference of two sets, okay, y versus e, and e is guaranteed to be in y. How do I know e is in y? Originally, e is in y. Okay. And actually, once we get rid of sigma, we really should be, we should get rid of the minus symbol over here, because once we get rid of sigma, there's no e anymore. So I really should do this step over here. Would this thing be the same thing as bar y bar minus 1? Can I establish this equality? Just focus on the highlighted portion. Would that make any sense? Knowing that e is an element in y, the cardinality of the difference of y and the set that only has e is really the same thing as the cardinality of y minus 1. Would that make sense?
If e's just one element.
Hmm?
If e's just one element.
Because e is guaranteed an element in y. So, okay, so once we can establish that, we can now just use bar y bar minus 1 in place of this. Okay, so get rid of that, get rid of that. Okay, so now we have this relatively simple, equation here. Okay, so now we go for the definition of permutations. Okay, so can someone tell me what is the definition of permutation? Some kind of factorial divided by some other factorial, right? So how do you define that? What is the numerator and what is the denominator?
N factorial divided by.
Okay, we don't have n here. We do have by y bar minus 1, right? Factorial of that divided by what? Y bar minus 1 minus k, right? Because we have this entire thing. So it's a little bit long. It takes a little bit of time to spell it out, but that's just from the top. That's from R itself. So we're taking the factorial of that, right? Okay. And then we have the bar, y bar on the outside, which means it also belongs to the numerator, right? So what do we do about this? Simplify. Okay, so what can we do to simplify this? Well, let's figure out what we can do with the top here. Okay, the numerator is this entire thing. Whoops. There we go. This is the entire numerator. What is, okay, it takes a lot longer to spell it out, but when you think about the concept, it's really easy. To spell it out, we're talking about what is bar y bar as one number times bar y bar minus 1, that whole thing's factorial.
Bar y bar.
Okay, well, yep, exactly. So the whole top or the whole numerator is just the factorial of bar y bar. Okay, there we go. What about the denominator? You just figure out what is the numerator. What about the denominator? This whole thing here. Let's see whether we can spell it out like this. Can we spell it out like that? I just move the subtract. I just group the minus 1 minus k into one term, okay, and then put the negation on the outside. So in the inside we have k plus 1, okay. But that looks oddly familiar. Okay, I'm okay. Just make sure that we have an exclamation point at the right place. Open, close. There we go. Okay, so that we got the right level of parentheses at the right places. Okay. What is that?
One, two, k plus 1.
It's the permutation, not choose. It's the number of permutations when you're given with bar, y bar things to choose from, but you're choosing k plus 1 things out of it. Isn't that what we were looking for? We're done. Now this proof looks really, really difficult to read because I cannot do all the symbolic stuff like sigma, omega, subscript, superscript. Yep.
On that, would you mind writing the one that says union on the board really fast?
Write it
Just how we would write that in our notes on the board.
on the board. How about I put it inside the my own document? Okay, so let's see how we can do this inside the document. Okay, we got 2 minutes. Well, do you think I can do it in 2 minutes? Mm-hmm. Okay, so the first thing we need to do is to make sure that the omegas, they start with a backslash. Union is not called union, it's called cub. Okay, and in needs a backslash. So I'm really just converting everything into the LaTeX format. Curly braces need to be escaped. Okay. Okay. And then whenever we see the equal to, if I want this to be on multiple lines, I want this thing here. So replace every single equal to. So replace. Probably can just do a global replace, search and replace here. So I'm just going to do this. The ampersand basically is a tab of some sort. So this way we can align the equal sign of everything. And then all the segments need to be backslashed. Okay. And all the ins need to be backslashed. And then all the curly braces, they all need to be escaped. And omega needs to be escaped. Escape, escape. The next class, usually the professor doesn't come in on time. I just want to make sure that you don't miss your next class also. That's all. Okay. I think that looks reasonably good. Okay, every time we have a division, we can also use fraction. So we have a fraction of this part and fraction for the second part. And open, close. Okay. So I think I got most of it, probably missed something. Begin EQN array as the beginning. And when we're done, we have an end EQN array, which stands for equation array. And every time we need a new line, it is a backslash backslash. Okay. And in Moodle, it doesn't like to have new lines. So we basically have to get rid of all the new lines. Okay. I think this is it. Okay, let me see if I can get to the end of line here. Yep. Okay. So we'll give it a try. I would be surprised if it works the first time, but we'll give it a try. This is not the entire thing either. It really is just the nastiest part of the proof, right? So I would definitely go and massage it, but I want to capture this part first because the other part is easy. It's just this part that's a little bit difficult. So we do it all. Sorry?
Is our exam still on Wednesday?
Monday. Yep. Okay, so what do you think? Do you think this is going to work or not? I have no confidence at all.
Never works on the first try.
Most of the time, if it does work the first time, it's not worth doing. Okay, it's close except for the multiplication and the Cartesian product. So the x and the asterisk. Yeah, backslash time for one, and then just a multiplication. But it came close. Okay, so it's close enough that we can understand.
Thank you. So when you're saying this thing from e to y, you're saying from e equals 1 to y?
This means that for every element e of y, do the following.
Because I was kind of confused because I'm doing series in calc right now. It always starts like from a number and goes to 1. So I'm wondering if e is starting at a number, or is just saying from e